Good evening, friends. Get comfortable and let's dive together into a story that began long before humans, cities, or even the very first organisms appeared. Tonight, we'll take a calm walk along a path that stretches back almost 4.6 billion years. But don't rush to fall asleep. This story hides far more dramatic twists than any movie, because, in theory, Earth was never really supposed to survive. Imagine it. Our world began as a molten sphere that could have been shattered at any second by the next asteroid. Its atmosphere could have slipped away into space. Its surface could have remained an endless ocean of lava. Even the birth of the moon was the result of an impact that could easily have put a full stop to the planet's future. And yet, Earth endured, and now we can calmly listen to its story before we go to sleep. Around 4.6 billion years ago, at the dawn of the solar system, the space was nothing but a cold, empty universe filled with gas and dust remnants from previous generations of stars. From this cosmic cloud, all the planets, including Earth, were formed. At that time, the solar system was far less stable than it is today, full of chaos, collisions, and destruction. Earth began its history as a molten mass, subjected to frequent impacts from asteroids and other cosmic objects. These collisions not only heated the planet, but also created the conditions for the formation of the first chemical elements, such as carbon, silicon, and oxygen, which became the foundation for the planet's future development. The process of Earth's formation was far from peaceful. Constant meteorite impacts and volcanic eruptions led to the entire surface of the planet being covered with oceans of lava. The atmosphere, composed of carbon dioxide and water vapor, was too hot and dense to support life as we know it. But it was in this chaos that the most important processes began, leading to Earth's stabilization and the creation of conditions necessary for life to emerge. Over time, after tens of millions of years of Earth cooling down, the first solid crusts began to form. The atmosphere started to change, and volcanic activity led to the formation of the first oceans. This process laid the groundwork for the further development of the planet and all future ecosystems. A key moment in Earth's history occurred about 4.5 billion years ago, a giant collision with a planet the size of Mars, which resulted in a large amount of material being ejected. This material gathered and formed the Moon, which continued to stabilize Earth's axial tilt and influence the planet's climate. This collision also created conditions that allowed Earth to remain within the habitable zone. After the formation of Earth, around 4.5 billion years ago, the planet continued to endure harsh conditions, frequent meteorite impacts, extreme temperatures, and magma oceans. However, it was during this period, following a giant collision between Earth and a Mars-sized planet, that a new phase in the history of our planet began, one that would forever change its development. As a result of this catastrophic impact, which nearly destroyed Earth's surface, a satellite was formed that would become known to us as the Moon. All the material ejected into space formed a ring of molten debris around Earth, which eventually gathered and coalesced into the Moon. This event became one of the most important factors in determining the planet's subsequent stability, as well as the conditions necessary for the emergence of life. For the first few million years, Earth remained extremely unstable and hostile to life. The atmosphere was filled with carbon dioxide, sulfur, and water vapor. This was a planet covered in fiery magma, with constant volcanic eruptions and ongoing impacts from cosmic objects. Surface temperatures were so high that water remained in the form of steam and oceans could not yet form. However, with each passing million years, Earth began to gradually cool. Volcanic activity led to the formation of the first continents, and water vapor began to accumulate in the atmosphere, slowly condensing into the first oceans. The atmosphere also underwent changes, with the production of oxygen and nitrogen, which would later create conditions necessary to support life. The Moon played a crucial role in these processes. Its gravitational pull stabilized Earth's axial tilt and provided regular tidal forces, which helped mix the oceans. This created ideal conditions for chemical reactions, which, over time, led to the formation of the first organic molecules, precursors to life. Earth's atmosphere began to form, and while the planet was still far from stable, it was slowly transforming into a place where life could eventually emerge. After Earth passed through a period of intense collisions and volcanic activity, the planet began to cool, and its surface began to take on a more stable appearance. This evolution led to important changes in its atmosphere, ultimately creating conditions suitable for life. As Earth began to cool, volcanic activity remained significant, but over time, the volume of carbon dioxide and other gases being released began to decrease. The planet's surface became covered by a solid crust, and the deep oceans started to fill with water, which also helped lower the temperature. During this period, the first atmosphere was formed, which was rich in carbon dioxide, ammonia, sulfur, and water vapor. These components formed the basis for the first chemical reactions, which played an important role in the origin of life. For Earth, this was a time of major transformations that lasted millions of years. The atmosphere began to change its composition, creating conditions for the formation of chemical molecules that would become the foundation for life. Water vapor molecules gradually condensed to form clouds, and liquid water began to accumulate on Earth's surface. This allowed Earth, for the first time in millions of years, to become a more stable planet, ready for the emergence of life. The influence of the Moon, with its gravitational pull, also became critically important for stabilizing conditions on Earth. The Moon helped regulate Earth's axial tilt, ensuring a more stable climate, which also played an important role in the formation of the atmosphere and the maintenance of liquid water on the surface. With each passing million years, although volcanic activity continued, it became less intense, and atmospheric conditions became more favorable for chemical reactions, which over time would lead to the emergence of the first organic molecules. These molecules, such as amino acids and sugars, became the building blocks for life. Earth gradually became a place where the process of chemical evolution unfolded, eventually leading to the creation of the first living organisms. As Earth's atmosphere stabilized and water in the oceans continued to gather and cool, the planet began preparing its surface for the emergence of life. This was a key moment in Earth's history, because it was in these conditions that life first emerged, setting the foundation for the future evolution of all life forms on Earth. With the development of a stable atmosphere and the formation of oceans, Earth became the ideal platform for the emergence of life. But how did this incredible transformation begin? It all started with chemical processes that took place in the waters of the primordial oceans, where simple molecules began to combine, forming increasingly complex structures. The key components of these chemical reactions were organic molecules such as amino acids, carbohydrates, and lipids. These substances, the building blocks of life, could have formed as a result of the energy provided by volcanic eruptions, lightning, and solar radiation. In the conditions typical of early Earth, these molecules interacted, forming more complex chemical compounds that became the foundation for the emergence of living organisms. One of the first steps toward life was the creation of molecules capable of self-replication. One such molecule could have been RNA, which has the ability to both store and transmit genetic information. Experiments like the famous Miller-Urey experiment demonstrated that organic molecules could form under conditions similar to Earth's early atmosphere through the action of electrical discharges. These molecules could have been the precursors to biological molecules, such as DNA, which plays a central role in biological processes. Initially, the molecules may not have been alive, but they possessed the ability to self-organize. Over time, they began to combine into more complex structures, such as protobionts, primitive cells capable of performing basic functions typical of living organisms, including metabolism and replication. Some scientists propose the RNA world hypothesis, suggesting that RNA molecules might have been the foundation of the first living forms. These molecules could not only store information, but also catalyze chemical reactions, allowing them to evolve, becoming more complex and capable of self-replication. With the development of these molecules, the process of biological evolution began, leading to the creation of the first living cells. Meanwhile, in Earth's oceans, other important chemical reactions took place, such as the formation of membranes, which became the foundation for cellular structures. All of this occurred over millions of years, until the molecules, accumulating in certain places in the oceans, began to form the first living cells. Thus, early chemistry on Earth created the conditions for the emergence of life, which, starting with simple forms, gradually led to the creation of more complex organisms. This was the beginning of evolution, which paved the way for the appearance of all life on Earth. Earth, as we know it today, began its journey over 4.5 billion years ago, and in its early stages, the planet was unrecognizable. This period is known as the Hadean Eon. At that time, Earth was a molten mass, covered by oceans of lava, and its atmosphere was a mixture of carbon dioxide, ammonia, and sulfur compounds. It was so dense and toxic that creating conditions for life as we understand it was impossible. On the surface of Earth, intense volcanic activity continued, and the planet was constantly bombarded by asteroids. Each impact shattered its surface, causing new catastrophes and destruction. However, with each such event, the planet gradually became more stable, its surface began to cool, and its atmosphere began to change. Volcanic eruptions during this period released massive amounts of gas and dust into the atmosphere, contributing to the formation of the first oceans, which slowly began to fill with water. This process continued for millions of years, and it was during this time that Earth's structure began to form, laying the foundation for life in the future. A key event in Earth's history during this period was a massive collision that occurred about 4.5 billion years ago. An object the size of Mars collided with Earth, ejecting enormous amounts of molten material into space, which later coalesced to form the Moon. This impact not only caused the creation of Earth's satellite, but also played a crucial role in stabilizing the planet. The Moon helped stabilize Earth's axial tilt, which later ensured a more stable climate, creating favorable conditions for life to emerge. The process of Earth's cooling continued, and solid crusts began to form, while the atmosphere began to undergo changes. The first signs of stabilization were the oceans, which slowly filled with water. Over time, the atmosphere became more suitable for life, and Earth's surface became less hostile. However, at this stage, it was still far from the world we see today. After Earth passed through its initial catastrophes and stabilized in the early stages of its history, its conditions remained extremely hostile. However, it was during this period that the most crucial processes occurred, shaping the future conditions for the development of life. One of the most important factors that played a key role in creating conditions for life was the formation of Earth's magnetic field. Deep within the planet, due to continuous tectonic and volcanic activity, its iron and nickel core began to form, starting to rotate and generate a magnetic field. This magnetic field became an essential barrier that protected Earth's atmosphere from solar winds, streams of charged particles that could have stripped away Earth's atmosphere, as happened on Mars. The significance of the magnetic field cannot be overstated, as it played a pivotal role in protecting Earth's future atmosphere from the destructive effects of cosmic radiation and solar winds. Without this magnetic field, it is likely that Earth would not have been able to retain its atmosphere in the form we see today, which would have made the existence of life as we know it impossible. At this time, Earth was a truly extreme environment. Its surface remained hot and unstable, and its atmosphere was toxic and unsuitable for most forms of life as we know them. Massive volcanic eruptions, explosions, and frequent meteorite impacts continued to destroy and reshape the planet. Nevertheless, under these harsh conditions, the first major geological structures, such as continents, began to form. While these early continents were small and unstable, they still became the foundation for the future formation of land masses, which would later be critical for the development of ecosystems. The oceans continued to fill with water, and the atmosphere, although still dense and toxic, began to change due to volcanic activity, creating the first signs of stability. Despite its hostile environment, Earth had already begun slowly preparing for more favorable conditions for the development of life, which would later allow chemical processes to lead to the formation of the first organic molecules. As Earth began to cool and its atmosphere and oceans stabilized, the conditions for the emergence of life gradually became more favorable. This was a critical moment in the planet's history, when chemical reactions occurring in the oceans led to the formation of the first organic molecules from which living beings later evolved. Initial molecules, such as amino acids and carbohydrates, began to gather into more complex structures, such as lipids and proteins, which formed membranes similar to cell walls. These molecules could unite to form the first primitive cells, protocells, which possessed the basic characteristics of living organisms, such as metabolism and the ability to divide. The first protocells, perhaps not fully living organisms as we understand them today, already had the property of self-replication, which became a key element in the evolutionary process. These molecules could reproduce themselves, passing on information and gradually evolving, leading to the formation of the first living cells. One of the most important steps in the evolution of life was the development of RNA, or ribonucleic acid, which was likely the first molecule with both information storage and catalysis of chemical reactions. The RNA world theory suggests that RNA molecules could have been the key component of early life forms, playing a crucial role in chemical evolution. RNA molecules could replicate themselves, allowing them to evolve and become more complex over time. Over time, these molecules evolved into more complex systems, creating protocells that eventually became the foundation for all living organisms on Earth. This process continued for billions of years, gradually leading to the creation of multicellular organisms, which became the foundation for all forms of life that exist on Earth today. Around 2.4 billion years ago, a key moment in Earth's history occurred: the Great Oxygenation event, when the amount of oxygen in the atmosphere sharply increased, leading to significant changes in both the composition of the atmosphere and life on the planet. Prior to this time, Earth's atmosphere was dominated by carbon dioxide, methane, and ammonia, with very little free oxygen. However, life began to play a role in this process. One of the most important factors was the emergence of cyanobacteria, microorganisms that began using sunlight to convert carbon dioxide into organic compounds and oxygen. This phenomenon, known as photosynthesis, allowed cyanobacteria to produce oxygen as a byproduct of their metabolic processes. Over time, the amount of oxygen in the atmosphere began to rise, triggering major changes on Earth. This was both a blessing and a curse. For anaerobic organisms, which could not survive in an oxygen-rich environment, oxygen became toxic. This led to mass extinctions of species that could not adapt to the new conditions. However, those organisms that could utilize oxygen began to evolve and develop new forms of life. The increase in oxygen levels also led to the formation of the ozone layer, which became a shield against harmful ultraviolet radiation from the sun. This made it safer for life to emerge on land, as the Earth's surface became much more hospitable for living organisms. The Great Oxygenation event played a crucial role in the evolution of life on Earth. It laid the foundation for the emergence of complex multicellular organisms and ultimately for the development of all higher forms of life, including plants, animals, and eventually humans. This process continued for many millions of years, but it was during this period that the groundwork was laid for all the life we see on our planet today. Around 700 million years ago, Earth experienced one of the most extreme events in its history, the Snowball Earth period. This era was characterized by the entire surface of the planet being covered in ice from the poles to the equator. The temperature on Earth was so low that the oceans froze, and a continuous layer of ice formed, enveloping the planet. This episode is one of the most mysterious and difficult to explain in Earth's history. What caused the Snowball Earth? Scientists believe the cause lies in changes in the composition of the atmosphere and solar activity. Earth underwent global cooling, which may have been triggered by a decrease in atmospheric carbon dioxide levels, driven by the activity of living organisms absorbing carbon dioxide, as well as reduced solar activity, since the sun was less bright at that time compared to now. Despite this, life on Earth survived. In the oceans, beneath the ice, vital ecosystems based on chemical processes, such as chemosynthesis, continued to thrive. In chemosynthesis, organisms use chemical energy rather than sunlight to synthesize food. These organisms managed to sustain themselves while the climate gradually recovered. Many scientists believe that it was during this period, in these isolated ecosystems, that more complex forms of life began to evolve. Eventually, Snowball Earth gave way to a warmer climate, and the planet returned to more familiar conditions. However, despite the extreme conditions, life not only survived but also adapted to the new circumstances, paving the way for further evolution. This period became a significant milestone in Earth's history, demonstrating how life on the planet can adapt and survive even under the harshest conditions. It also set the stage for the future evolution of multicellular organisms and prepared the ground for the Cambrian explosion, when life on Earth became significantly more complex and diverse. Around 540 million years ago, one of the most significant events in the history of life occurred on Earth: the Cambrian explosion. This period marked a time of rapid increase in biodiversity, when a vast number of new life forms appeared on the planet, many of which are ancestors of modern animals. Before the Cambrian explosion, life on Earth was primarily composed of microscopic, single-celled organisms. However, with the onset of the Cambrian period, around 541 million years ago, a radical leap in evolution took place. During this time, multicellular organisms began to evolve into various life forms with more complex anatomy, allowing them to occupy new ecological niches. This was the moment when life on Earth transitioned from simple forms to complex, multicellular beings with specialized organs. Multicellularity, or the ability of cells to function as part of a single organism, was one of the most crucial steps in evolution. Unlike single-celled organisms, multicellular organisms could divide functions among cells, giving them a significant advantage. For example, different cells could specialize in food absorption, defense, reproduction, and other vital processes. This allowed multicellular organisms to become much more complex and diverse. The Cambrian explosion was also a time when the first vertebrates appeared, such as fish with backbones, as well as hard-shelled organisms like trilobites. This event laid the foundation for the further evolution of all major animal groups, including invertebrates, fish, amphibians, reptiles, mammals, and birds. During this time, the first predators and prey emerged, leading to the development of complex ecosystems and food chains. The process of generating such a diverse range of life forms was made possible by the accumulation of genetic changes that occurred over the previous billions of years. These changes allowed organisms to adapt to new environmental conditions, and as a result, biological diversity rapidly expanded. The Cambrian explosion was the moment when life on Earth began to evolve in the form that we know today, creating the foundations for all subsequent stages of evolution, including the emergence of more complex life forms and ultimately humans. After the Cambrian explosion, when life on Earth became significantly more diverse, a new stage in evolution began, marking an important transition: the conquest of land by animals. This event occurred around 360 million years ago, when the first vertebrate animals began to leave the water and conquer new territories. Before this time, all life on Earth existed in the aquatic environment, where the emergence and development of animals, such as fish and marine invertebrates, took place in response to changing conditions. However, with the development of respiratory systems and the ability to move on land, animals began to seek out new ecosystems to secure food, avoid predators, and find more favorable conditions for reproduction. The first animals to leave the ocean were amphibians, ancient ancestors of modern frogs, salamanders, and crocodiles. These organisms had a number of adaptations that allowed them to breathe air and survive in environments that were once dominated only by the ocean. Amphibians developed lungs, which allowed them to breathe oxygen, and their skin, while still capable of gas exchange, became more resistant to the external environment. As amphibians evolved, life on land gradually became more complex. Some groups of animals began to develop adaptations to protect themselves from heat and drought, which allowed them to thrive in environments with fluctuating temperatures. The development of teeth and claws, along with the improvement of movement using 4 limbs, allowed animals not only to move, but also to actively hunt and defend themselves from predators. The conquest of land took place in several stages. Initially, amphibians were restricted to wet areas, such as swamps and rivers. However, with the evolution of reptiles, animals were able to colonize drier and more diverse ecosystems. Unlike amphibians, reptiles developed more durable, waterproof skin, and their eggs with hard shells enabled reproduction in dry conditions, making it possible for them to spread across the land. The conquest of Earth by animals became a crucial stage in evolution, as it opened up new ecosystems and accelerated the development of new species adapted to different conditions. This allowed animals to become the dominant inhabitants of land, creating the foundation for further evolutionary changes that ultimately led to the emergence of dinosaurs, mammals, and birds. The Carboniferous period, which lasted from 359 to 299 million years ago, was one of the most significant periods in Earth's history. This era was marked by the emergence of giant, oxygen-rich forests and the development of large ecosystems that played a key role in shaping the planet as we know it today. During the Carboniferous, Earth's climate was warm and humid, which fostered the growth of vast, swampy and forested ecosystems. These forests were home to massive coniferous plants, ferns, and mosses, all reaching enormous sizes. These plants, due to the high levels of carbon dioxide in the atmosphere, grew rapidly and became increasingly diverse. A defining feature of this period was the development and spread of the first large trees. These trees, which were part of ancient coniferous and fern-like plant families, were incredibly tall and robust. They formed dense forests that, in turn, created new ecological niches for animals such as insects, amphibians, and the first reptiles. The Carboniferous was also a time of giant insects, such as dragonflies with wingspans up to 70 centimeters appeared. One of the most important ecological events during this time was the accumulation of carbon released by plants in the atmosphere and soil, as the plants actively absorbed carbon dioxide, maintaining high levels of oxygen in the atmosphere. This oxygen, in turn, allowed for the development of larger organisms. During this period, giant life forms like massive spiders and millipedes emerged, which is thought to be linked to the high levels of oxygen in the air, enabling these creatures to grow to such large sizes. However, despite these favorable conditions, the Carboniferous was also a time of global climatic changes. As vegetation increased and absorbed more carbon, there was a significant alteration in the composition of the atmosphere. This process resulted in the accumulation of carbon, which contributed to the formation of vast coal beds. Coal, formed from decaying plants, was the first significant carbon accumulation, which would later play a crucial role in the energy history of humankind. Earth during this period was covered in massive tropical forests where life thrived, creating powerful and complex ecosystems. These forests became the foundation for the formation of coal deposits, which began to accumulate in conditions where much of the vegetation died, absorbing and trapping carbon in sedimentary layers. The Carboniferous was a time of great biological achievements, as plants and animals reached new levels of evolution. However, as the period came to an end, Earth faced climatic and ecological changes that paved the way for the next significant era, the Permian period. The Permian period, which lasted from 299 to 252 million years ago, marked a time of significant changes on Earth. It was an era of evolutionary flourishing, during which many groups of animals and plants developed. However, it was also at the end of the Permian period that one of the largest mass extinctions in Earth's history occurred, the Permian mass extinction. Known as the Great Dying, this event became the largest catastrophe in the history of life on Earth, wiping out approximately 90% of all marine species and 70% of terrestrial animals. The causes of the Permian extinction are still debated by scientists, but several factors likely played a key role in this catastrophe. One of the main factors is believed to be volcanic activity. Toward the end of the Permian period, massive volcanic eruptions, particularly in the Siberian region, released huge amounts of carbon dioxide and sulfur into the atmosphere. This triggered dramatic climate changes, including a global temperature increase and significant alterations in the composition of the atmosphere. The high levels of carbon dioxide led to the greenhouse effect, causing the planet's temperature to rise and oxygen levels in the atmosphere to drop. At the same time, sulfur emissions resulted in acid rain, which had devastating effects on ecosystems, particularly marine flora and fauna. This created an oxygen deficiency in the oceans, severely impacting marine species. Earth underwent catastrophic changes in climate and ecosystems, and only a few species of animals and plants managed to survive. Among those that survived were reptiles and some plants. Soon after the Permian extinction, a new phase of evolution began on Earth. The recovery of ecosystems took millions of years, but eventually, new forms of life emerged. The impact of the Permian extinction on the future of life on Earth was twofold. On one hand, it reduced the diversity of life and created vacancies in ecosystems, but on the other hand, it opened up new opportunities for evolution. The reptiles that survived this period became the dominant species during the Mesozoic era, with dinosaurs, which began to develop during this period, emerging as some of the most successful and largest animals to ever live on Earth. This extinction event paved the way for the differentiation of new species, as the ecological niches left open by the extinction were quickly filled by new organisms. Earth's life systems began to recover, and millions of years later, Earth entered a new era filled with new life forms and new ecological interactions. After the Permian extinction, which left the planet in ruins, life began to slowly recover, paving the way for new forms of evolution. The Triassic period, 252 to 201 million years ago, marked the time of this recovery, as well as the emergence of dinosaurs, some of the most successful and dominant animals in the planet's history. The return of life after the Permian extinction was gradual. Ecosystems began to recover, and through evolution, new species of animals and plants adapted to the changing conditions. One significant aspect of this recovery was the development of reptiles, which were able to occupy ecological niches that had been left empty after the extinction of most animals. The most important event of this time was the emergence of dinosaurs, which began to evolve during the Triassic period. Dinosaurs, like their predecessors, reptiles, evolved in conditions where the climate was relatively warm and the atmosphere was rich in carbon dioxide. They became the dominant land animals due to their characteristics: a more efficient breathing system along with strong developed muscles that allowed them to be fast and aggressive predators or magnificent herbivorous giants. Dinosaurs appeared during the Triassic period and immediately began to occupy increasingly larger territories. At the beginning of this period, they were relatively small in size, but over time, as evolution progressed, some species grew to be gigantic. This group of animals was incredibly diverse, including predators such as Archaeopteryx and Megalosaurus, as well as huge herbivores such as Triceratops. A key moment for dinosaurs was their ability to move on 2 or 4 legs, which allowed them to adapt to different environments. One of the most important factors in their success was their aggressive behavior and high speed, which not only helped them survive, but also enabled them to dominate in various ecosystems. The spread of dinosaurs across the planet was also accelerated by the gradual breaking apart of Pangaea, the supercontinent that held all of Earth's land masses at the time. This separation led to the formation of new ecosystems and climate zones, which stimulated the further development of various groups of dinosaurs as well as other animals and plants. In addition to dinosaurs, other reptiles developed during this period, such as pterosaurs, the first flying reptiles, and ichthyosaurs, which began to evolve in marine environments and occupy new ecological niches. The ecological role of dinosaurs was immense. They not only became the primary predators and herbivores in ecosystems, but also played an essential role in the carbon cycle. Through their activities, along with the development of vegetation, the Earth's atmosphere remained enriched with oxygen and carbon dioxide. This helped stabilize the atmosphere and maintain a relatively warm climate, which in turn promoted further life development. During the Triassic period, many plant groups, such as palm trees and ferns, also emerged and became important sources of food for the dinosaurs. These plants, along with a well-developed flora, provided the necessary nutrients for dinosaurs and helped maintain the balance of ecosystems. Thus, the Triassic period was not only a time of life recovery after the Permian extinction, but also a period of triumph for the dinosaurs, who began to rule the Earth and laid the foundation for the further evolutionary path on the planet. At the end of the Cretaceous period, around 66 million years ago, Earth experienced one of the most significant and catastrophic events in its history: the Cretaceous extinction, which led to the disappearance not only of the dinosaurs, but also many other groups of living organisms. This extinction became the last of the 5 major mass extinctions on Earth and marked the beginning of a new era in the planet's history. The causes of the Cretaceous extinction are still debated among scientists, but the most widely accepted hypothesis suggests that this extinction was caused by a collision between Earth and an asteroid or comet, which devastated the planet's ecosystems. This impact caused a massive explosion, ejecting enormous amounts of dust and gases into the atmosphere, which led to a significant drop in Earth's temperature, known as the nuclear winter. The dust and soot in the atmosphere blocked sunlight, causing a sharp cooling and the cessation of photosynthesis, which had a catastrophic effect on plant life and animals. In addition, volcanic activity at the time, especially in the region of modern-day Siberia, also played a role. The Siberian traps, vast volcanic areas that emitted significant amounts of carbon dioxide and sulfur into the atmosphere, intensified the greenhouse effect, contributing to climate change. This also led to shifts in ecosystems, making conditions on Earth even harsher for many species of animals. The consequences of this catastrophic event were devastating. Dinosaurs, which had been the dominant life forms on Earth for 160 million years, vanished. While some small dinosaur species, such as birds, survived and evolved into the modern group, the majority of dinosaurs, including the largest predators and herbivores, disappeared. Life on Earth endured a serious interruption, but after the Cretaceous extinction, it began to recover, and a new era, the Age of Mammals, began, with major changes in Earth's ecosystems. Mammals, which until that time had been relatively small creatures, began to occupy ecological niches that had been vacated after the extinction of dinosaurs. The rise of mammals and the development of new groups of animals after the extinction of dinosaurs led to a rapid increase and diversification of species. During this period, important groups of animals, such as birds, beasts, including the first large mammals, and primates began to evolve. This process, in turn, led to new evolutionary advancements and the formation of more complex ecosystems. The return of life in the oceans after the extinction was also a key moment. Marine reptiles, such as ichthyosaurs and plesiosaurs, disappeared, but new marine life forms, including whales and sharks, began to develop. Marine life adapted to the new conditions, and despite the extinction of many species, it began to thrive again. Thus, the Cretaceous extinction not only marked the end of the age of dinosaurs, but also the beginning of a new era, the era of mammals and birds, during which entirely new forms of life emerged on Earth. This event radically changed the course of evolution on the planet, opening up opportunities for mammals, which in the future, including humans, would come to dominate the Earth. After the extinction of the dinosaurs at the end of the Cretaceous period, Earth entered a new era in which mammals became the dominant life forms on the planet. This was a time of profound changes in ecosystems, as life on Earth began to recover from the catastrophe caused by an asteroid impact, as well as volcanic activity that darkened the sun and altered the climate. Immediately after the extinction of the dinosaurs, Earth's ecosystems were significantly disrupted. However, with the disappearance of most large predators and herbivores, animals that had previously been small and inconspicuous began to evolve and occupy the ecological niches left vacant. Mammals, which had previously been mostly small, nocturnal creatures, began to grow in size and diversify. Initially, mammals continued to evolve in various forms, adapting to new conditions. Mammals were much better suited to climate and ecosystem changes than other groups of animals. They also had unique adaptations, such as warm-bloodedness, which allowed them to regulate their body temperature effectively and survive in various environments. This ability was especially important after Earth experienced a series of sharp climate changes, including cooling and fluctuations in oxygen levels. The evolution of mammals after the extinction of the dinosaurs also led to the appearance of the first primates, a group of mammals that would later give rise to the human lineage. Primates began to develop more complex brains and unique social structures, which played a key role in the future development of human evolution. During this period, there was also a flourishing of vegetation. After the extinction of the dinosaurs, plants, such as flowering plants, began to expand, filling the ecological niches left by the extinct animals. Flowering plants were important not only for the development of ecosystems, but also for mammals, as they became a primary food source for herbivorous animals. The climate also began to stabilize after the global changes caused by the extinction event. Earth stopped experiencing such extreme climatic fluctuations, and conditions on the planet became more stable for life, which allowed various groups of animals to develop and evolve. During this period, mammals began to significantly increase their diversity, occupying new ecosystems, including forests, savannas, and deserts. They began to actively develop different survival strategies, from large herbivores like early elephants and mammoths to predators like saber-toothed tigers and hyenas. This period laid the foundation for the further development of life on Earth. Mammals, birds, and plants, and other groups of organisms continued to evolve, leading Earth toward the present day. After mammals began to dominate Earth and ecosystems stabilized, life on the planet took new forms, and among the mammals, the first representatives of the Homo genus began to appear, the ancestors who would eventually become humans. The evolution of humans is a long and complex process that began around 6 to 7 million years ago. In the early stages, humans and their ancestors resembled other primates. However, with development and adaptation to new conditions, humans developed unique traits that distinguished them from all other animals. The emergence of the first hominids occurred in Africa, where the climate and ecosystems were changing and forests gradually gave way to savannas. Hominids such as Australopithecus began to adapt to life in open spaces. This led to changes in their physical appearance. They began walking on two legs, which allowed them to move more efficiently over long distances and freed their hands for tool use. One of the key factors that contributed to human evolution was the ability to use tools. The first primates used stones and sticks for gathering food, defending against predators, and other needs. These primitive tools marked an important milestone in evolution, as they enabled the ancestors of humans not only to survive, but also to enhance their ability to adapt to changing conditions. As hominids evolved, their brains increased in size, leading to more complex social structures and cognitive abilities. The development of the brain Particularly, the enlargement of the areas responsible for speech and information processing played a crucial role in shaping human skills and culture. Around 3.5 million years ago, the first representatives of the Homo genus, such as Homo habilis, appeared on Earth. They already used more sophisticated stone tools, which differed from the more primitive tools of their predecessors. This marked the first step in the creation of a culture based on cooperation, learning, and innovation. Approximately 1.9 million years ago, Homo erectus, the first human-like species that resembled modern humans more closely, emerged on Earth. Homo erectus was already able to use fire for cooking, greatly improving its chances of survival in different climatic conditions. It was also the first species to leave Africa and begin spreading across Eurasia, playing a significant role in the expansion of humanity across the planet. Human evolution continued, and around 300,000 years ago, Homo sapiens, modern humans, appeared on Earth, dominating the planet. Homo sapiens was distinguished not only by highly developed tools, but also by flexible social structures, language development, and cultural achievements that allowed them to build complex societies, cities, and civilizations. With the emergence of Homo sapiens on Earth, a new era in human history began. However, the path of human evolution was not direct or unchanging. Humanity had to face a series of ecological and climatic challenges, including numerous ice ages, which had a profound impact on the development of human populations and their adaptation to changing conditions. The ice ages, alternating with warmer interglacial periods, presented many challenges for early humans. For example, the Pleistocene epoch, around 2.6 million to 11,700 years ago, was a time when significant climatic fluctuations occurred on the planet. During this period, massive glaciers covered the northern parts of the continents, and temperatures were much lower than today. For Homo sapiens, the Ice Ages represented a time of harsh trials, as living conditions on Earth became more severe. The cooling temperatures, disappearance of vegetation, and the reduction of animals that served as food all required humans to be incredibly flexible and adaptable. One of the most important adaptations developed by humanity in response to the cold climate was the use of fire. Fire not only allowed humans to stay warm, but also provided protection from predators, improved digestion, and allowed for food preparation, which helped to enhance nutrient absorption. This was a crucial step in the development of culture and social life for early humans. Another key adaptation was the development of clothing. People began to make clothing from animal skins, which helped protect them from the cold. This also allowed humans to expand their habitat range and venture into more northern areas of the planet, such as northern Eurasia and North America. In addition, the development of tools became essential for survival during the Ice Ages. Humans began to use stone and bone tools for hunting, fishing, food processing, and shelter construction. This allowed them to adapt effectively to the cold climate and create more complex social structures that supported collective survival. With the development of hunting and gathering skills, as well as the shift from purely survival practices to cultural progress, early humans began to build settlements and cave shelters which protected them from harsh weather conditions. These settlements helped strengthen social ties and fostered the development of more complex cultural and religious practices. The development of language and symbolic culture became another important aspect of human adaptation. During the Ice Ages, when survival depended on the ability to work together, language became an invaluable tool for coordinating actions, transmitting knowledge, and strengthening social bonds. Archaeological findings, such as cave paintings and burials, show that early humans began to develop complex cultural traditions that played an important role in their lives and survival. Thus, the Ice Ages marked a significant stage in human evolution where survival depended on the ability to adapt to changing conditions. This period was also one of cultural and technological progress, which prepared Homo sapiens for further development and dominance on Earth. With the development of civilization, Homo sapiens began to exert an ever-increasing influence on the planet. These changes became particularly noticeable in the last few thousand years, when humans learned not only to use natural resources, but also to alter the very structure of Earth's ecosystems. The development of agriculture, industry, technology, as well as urbanization and globalization, led to significant changes in the climate, ecosystems, and the biosphere. The process of anthropogenic impact on the planet began with the earliest stages of settled life. One of the most important milestones in this process was the transition from hunting and gathering to agriculture. Humans began actively cultivating the land, clearing forests, plowing the soil, and raising domesticated animals. This change in lifestyle formed the basis for the further growth of the human population, but also led to significant ecological changes. The Industrial Revolution in the 18th and 19th centuries marked the next crucial stage in human impact on Earth. With the rise of industry, mass exploitation of natural resources like coal, oil, and gas began, leading to a significant increase in the emissions of carbon dioxide and other greenhouse gases into the atmosphere. This, in turn, caused global warming and climate change, which, according to scientists' predictions, may have long-term effects on the planet. Ecosystem degradation also became a consequence of human activity. Deforestation, water pollution, destruction of natural habitats, and changes to natural landscapes led to a sharp decline in biodiversity. Many species of animals and plants found themselves under the threat of extinction, disrupting the balance of ecosystems and potentially leading to irreversible consequences. Climate change issues have become central to discussions about the future of Earth. Rising temperatures, melting glaciers, rising sea levels, changes in precipitation, and extreme weather events all these effects of anthropogenic activity pose a threat to the survival of both humans and other species on the planet. However, humanity is also aware of these challenges and is taking steps to overcome them. The development of sustainable agriculture, renewable energy sources, solar, wind, hydro, biodiversity conservation, and efforts to reduce carbon emissions are important steps toward ensuring a more sustainable future. Moreover, technological innovations in the field of ecology, such as global climate and ecosystem monitoring, carbon capture technologies, and natural resource conservation, could play a crucial role in mitigating the impact on the planet and ensuring the resilience of human civilization in the future. A key challenge for future generations will not only be combating the consequences of anthropogenic changes, but also finding ways for harmonious coexistence with nature. This will require global cooperation, the development of new technologies, and the adherence to principles of sustainable development at all levels of society. Thus, humans continue to impact the Earth, and each year this influence becomes more noticeable and complex. The question of preserving the planet and its ecosystems will face humanity throughout the future. It is important to remember that the actions we take today will determine the state of the planet in the years to come. We have come a long way, from cosmic dust to the emergence of human beings. Earth has survived impacts, frozen nights that lasted millions of years, fiery ages of volcanoes, extinctions and rebirths. Every time it seemed like the end, it found a new way to keep the story going, through a sudden spark of life in the ocean, or through forests that once covered bare continents. Today, we humans have become the new force that is changing the planet faster than any asteroid or volcano. We can light up the night brighter than the stars, lift machines heavier than birds into the sky, and redirect rivers and reshape entire landscapes to suit our needs. How we treat Earth from this point on will determine what its next chapter looks like. Will it be the story of a species that understood its responsibility and learned to live in harmony with its planet? Or just another dramatic twist that future intelligent beings will one day study as yet another great extinction? Thank you for spending this evening with me. I hope this story has helped you see our planet a little more deeply and feel how fragile and at the same time how incredibly resilient it really is. Good night, and as you fall asleep, take a moment to imagine how slowly the pages of Earth's history turn, and how one of those pages is being written by us right now.